Why isn't this on? Oh dear. Can you see okay from there? And
Yeah.
Who keeps calling me? Don't want to talk. Right. There we go. Let's start. What did you have this morning? Did you have maths today?
That's chemistry.
And chemistry? What are you doing in maths? Still doing the differential equations? Inverse function. What am I looking for? Physics. Fields. Kepler's laws. Okay. Let's get started. Alright, if you can write that down. Kepler's laws. Where is my pen gone? Okay, you got that? Kepler's laws? Okay, so couple of things to do. So you know, if you're important in physics, you have 3 laws. Newton has 3 laws, you know. So Kepler has 3 laws as well. Some of these laws are very, very easy. Like the first law, Kepler's First Law. And all these laws have to do with planets. You know, sun, earth, moon, all these. Kepler's First Law says bodies in orbit of the sun, or other large masses, will move either in a circular path or an elliptical path. Now that's pretty obvious. So either something will move in a circle or elliptical, which is this shape here. Somebody desperately wants to get in touch with me. I better answer this because maybe somebody's sick or something. So just write that down, okay, and draw the picture. Hello? Yeah, I'm just in class at the moment. Everything okay? Oh, did he? Okay. I'll give you a call this evening, so. Alright. One of my uncles is very sick. Okay. So, you know this word circular means moving in a circle, or elliptical, which is this shape here. Okay. But you probably knew that already. Right? It's not some new information I'm giving you. Happy? Got that? Oh, Andy, did you find out what was wrong with your eye?
Yes, it was a sty. Well,
It is. You're dealing with it.
Yeah. It was here last week.
You saying it moved?
Yeah.
Dude.
It was fine for like 2 days, and then the next day, after that, suddenly it's here.
Yeah. You know what's funny? I don't know why. This is true. About 1 physics student per year gets a sty.
Yeah. So you can get as well.
Yeah, and then I had a student last year as well. I don't know what it is about being a physics student, because it doesn't happen to the biology students. So, it's quite peculiar. Anyways, that's Kepler's first law. Now, you can actually prove this law using, the proof is too difficult for us to do, it's a university proof. You can prove this using Newton's law here. But what's interesting is Kepler was before Newton. So the way Kepler figured this out is he looked at a lot of data on the movements of planets. And, you know, after looking at all this data and looking at all the graphs he could make, he could see that all the planets were moving in this shape. So this is his first law then. Okay, right. Kepler's second law states that the area swept out by an orbiting body per unit time is constant. Now, you can actually say that a couple of ways. Mathematically, the easiest way to change this into a statement is V1 or 1 equals V2 or 2. I'll explain what that means now in picture. Did anybody see Captain Marvel?
Yeah.
Any good? Give it a grade.
I would give it 9 out of 10.
Ah, that's good.
It's better than I expected, so that's good.
Okay.
I thought that that was the after film hype, so some morphine you gotta wear off this.
I see, okay. You saw it anyway. No one else saw it? You going to? No? Don't think so.
Which one?
Captain Marvel.
Is it new?
Oh yeah, very new. Like, what, last week or something? Yeah. Okay, did you get that? So, what this means, I can show you here with a picture. So it doesn't, where's my pen? There. It doesn't matter what the time is. So for example, you could look at months, alright? If you were to draw this shape here, this kind of triangle, which represents the movement of the Earth in 1 month. So for example, this could be June to July, for example, okay? And if you were to look some other time in the year, you know, maybe this is January to February, this area and this area will be the same. Now, what does that actually mean? So, because this is further away from the sun, and this is closer to the sun, then this distance here, will it be bigger or smaller than this? What do you think? Is this bigger or smaller than this? Bigger. But it's still the same time, 1 month. So it must be moving faster. So in other words, the closer it is to the sun, the faster it moves. And when it's out further, like here, is when it's moving slowest. So the speed isn't constant. It's like slow, slow, faster, 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 fastest, and then starts to slow back down again, and it's slowest here. And you can relate it using this formula. So imagine here this is V1 or 1, then that will equal over here, say V2 or 2. Or it doesn't matter, you can say V1 or 1 equals V2 or 2 equals V3 or 3 equals V3 or 3, V4 or 4. You get the idea. That if you multiply the V and the or, it's constant, it doesn't change. Okay, that's one way to state Kepler's second law, and this picture is nice. Let us prove the result above. No, let's not. Because in the exam, it's only Kepler's third law that you need to know the proof of. Okay, so you can just write this down and we'll do the proof. We'll do the third one now. You have all of this, Siba? And you have the picture as well? A picture would be helpful too. Chicken burger today? How often do you think you have a chicken burger?
Not a lot.
It seems like every time I ask you though.
Yeah, what about fries?
Huh?
You like their chips?
No, she doesn't eat the chips.
I eat them just the way I didn't eat.
Just the burger? Yeah. Okay, you got that, everyone? Yeah? So Kepler's third law now. Now, Kepler's third law states that the periodic time squared is proportional to the radius cubed. Or in other words, t squared is proportional to r cubed. So, if you double the radius, then the t squared gets multiplied by 8 times bigger. This is a little bit difficult, so you can actually write as a formula, and the formula is like this. T squared is 4 pi squared over gm r cubed. Now, note, hey everyone, note, this formula is not in the book, because in the exam they sometimes ask you to prove this formula. That's why it's not in the book. Okay, so I'm going to do the proof in a moment, but please make a note that this is not in the formula book. Yeah? Okie dokie. Yeah? The proof is on the exam and it's not in the formula book. So I'm going to have a look at the proof of this now. When Chow's ready. Chow, yeah. Okay. Now, the proof. So we'll just start off with, we'll say there's M, that could be like the sun, and there's M, small m, that could be like the earth, and it's moving around in a circle here. So, there's a force here. You know, because this is moving in a circle, F equals m omega squared r, right? But you also know from last week F equals g m over r squared. So we could make these equal. We could say m omega squared r equals g m over r squared. I'm going to cross multiply. Well, firstly, I can cancel this m with this m. I can bring this as omega squared equals gm over r cubed. So what I'll do is I don't want to go to a new page, I'll just put it over here. I'll say r cubed over gm equals 1 over omega squared. Sorry, I'm bringing the r cubed up and the gm down. Now here comes the trick. Or, well, squared, wasn't it? Yeah. Here comes the trick. I'll multiply the left and the right by 4 pi. Can anybody see what 4 pi over omega squared is? 4 pi squared over omega squared. Can anyone see what that is? Well, remember, what does t equal? 2 pi over omega. So what's 4 pi squared over omega squared? It's t squared, isn't it? T squared equals 4 pi squared or cubed over gm. And that is it, isn't it? Yeah. So that's Kepler's formula. That's the proof. That's the shortest proof I can think of. You have all of this, Siva? Yeah. Oh, she's such a bully, isn't she? Such a bully. She punches you with the pen. She says she doesn't like math. Such a bully. She gave her sty to Andek.
Oh my god. It was cute. But she gave me pills, so she's fine.
Okay, alright. She hooked you up with your pills. Yeah. Alright, do you have this? Yeah. Now, this is what I think is actually amazing. Kepler figured this out. Kepler existed before Newton. So before Newton, Kepler came up with this formula. Now that's really amazing because there was no mechanics. There was no F equals ma. That he figured this out by just looking at the data. You know, and I think that's pretty impressive. That he had the imagination to figure this out when there was no theory. You know, it wasn't until Newton, until we had F equals ma and momentum and all this. So, you know, I think Kepler doesn't get enough credit. Newton gets all the credit. I think Kepler did a good thing. And you were asking me last time, Chow, about how could we know the mass of the sun, as an example. So if you look here at this formula, here's the sun, and you don't know its mass, right? And here's the Earth, and Earth goes around it. Okay, now, do you know the T here for the Earth to go around the sun? Of course you do. It's 365 days. If you know the T, and you know 4 pi squared and g, then you can get the m if you know the r. And the r is not difficult to calculate because people have known this information for a long time. So the way you can do it, I can't remember who it was, but anyways, what you could do is you could use your telescope to look at the sun, and then you could, I don't know, can't remember how they do it, but it's something like they take two different measurements at two different times of the year, you know, and they get this angle. I can't remember exactly, but they use the sine and the cosine rule, and they can get the distance. I don't remember how they actually did it. So you could know the radius. So then you can know the mass, which is quite... So this is what you were asking me the last time. How could you know the mass? And the answer is from this formula. Okay. So we'll look at an example now, but like I said, this is a very useful formula. So let's have a look at an example. Oh yeah, before we do, just one more definition. Does anybody know the meaning of this? A geostationary orbit is also called a parking orbit. Does anyone know this? Have they heard of it before? No? Well, what's the word orbit? Yeah, so this is like an orbit. So what do you think they might mean by a parking orbit or geostationary orbit?
Is it stationary in its position?
Yeah, but how can it stay stationary if it's supposed to be moving? So you have the right idea. It's something about it not moving, but in a very particular way. So look, this is what it means, for example. Here you are standing on the Earth, and the Earth obviously turns around this way. And here's a satellite in orbit, and it turns around the same as well. If the time here is the same as the time here, so that is 1 day, then what will happen is it will look like this is always above you, except it's actually moving with you, but it looks like it's not moving. So this is why we call it a parking orbit, because it looks like it's parked in the sky. Do you understand? Yeah. Now I think, I'm not sure, pretty sure though, that GPS satellites are in parking orbit. So the way the GPS works is they look like they're fixed in the sky, and your phone uses their position to calculate where you are. You know, so for example, maybe you have a GPS here and a GPS here, and this sends one signal, so this would say signal 1, and this sends signal 2. So your phone goes, signal 1 is above Ireland, signal 2 is above Ireland. So if I calculate these angles, I can know my position. This is the basic idea for the GPS, okay? So it's important for that. So it means that the orbit around the Earth, or whatever, has the same time as 1 day. That's what it means. It's a 1 day orbit. Got that? Yeah? Right. So here's an example. A small satellite is in a parking orbit around the Earth. So what do we know so far if I tell you it's in a parking orbit around the Earth?
Has 1 day.
1 day. What's 1 day exactly?
24 hours.
Oh, what I mean is what letter is 1 day? The T, the big T. How far is it from the surface of the Earth? And I tell you the radius of the Earth is this and the mass of the Earth is this. So I'll draw the picture. What you know, you have the Earth and you have your satellite. And I want to know what is this distance. And I tell you the time is 24 hours. Okay. I give you the mass of the Earth. It's 5.97 times 10 to the 24. Okay. I give you the radius of the Earth. The radius is 6371 kilometers. Yeah, and my question is, what's the h? So, I've only given you two formulas today. I've given you Kepler's third law and Kepler's second law. So which one is it that you think you need to use here? Which one? Kepler's second or Kepler's third? Yeah, because you know the T, you know the M, you don't quite know the radius, because the radius is here to here. So I'll call this radius of Earth, and you want, if you could work out that, and then minus this, you can get the height. Do you think you can do it, or do you want to see it? I see some people have calculators already, so I'll let you try it first. So I want the h here. Okay. Got an answer? It's very big, isn't it? Yeah. No, that's the surprising thing about these calculations. If you want a satellite to be in a parking orbit, it has to be really high up. Really high up. So what did you get? You can give it to me in kilometers. 1,000 kilometers, yeah. Yeah, which is a lot, isn't it, Matt? Because the Earth here is only 6,000 kilometers. So these GPS satellites, they're in very high orbits. Very high orbits. Let's calculate here. T, what's it? T squared equals 4 pi squared over gm or cubed. Yeah? Isn't that the formula? Isn't it? Yeah. So r cubed is equal to gmt squared over 4 pi squared. So r is the cube root of that. Now that r, by the way, guys, that's the r from here to here. But I want this distance, the h. So the h will equal cube root gmt squared over 4 pi squared minus 6371000. So let me put in the numbers. This is cube root 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 over 4 times 3.1415 squared minus 6371000. Oh, sorry. Flip it. I forgot to put in the time. Times 24 times 3600 squared minus 6371000. You have this math, you said it was like 35,000 or something?
35,856.
Yeah. Now, Matt, could you take out your phone and Google altitude of GPS satellite?
Approximately 28,000 km.
Okay, so I guess the GPS satellites aren't as high as I guess the GPS satellites aren't in geostationary orbit. Approximately 20,000. Oh, I'm so sorry. I told you a dirty, filthy lie. Earlier I said the GPS satellites are fixed in the sky. They're not. According to that, they actually move slowly in the sky. So it sounds like they have an orbit of 12 hours, not 24 hours.
Each satellite circles about twice a day.
Yeah, so its orbit is 12 hours then, not 24. So maybe it's the TV satellites that are geostationary. Sorry, should have an altitude of TV satellite. Maybe that's the one.
35,000.
There we go. Okay, all right. Yeah, that's the parking orbit. All right, so it's the TV satellites that are in geostationary orbit, not the GPS. Okay, can I continue? Yeah. Right, we have one question, but it's pretty big. The planet Mars is about 228 million kilometers from the Sun. One Mars year is 687 Earth days. Question A, what is the mass of the Sun? That's the first question. So, I'll just draw the picture. Here's the Sun. Here's Mars. Obviously, it's not to scale. The Sun is much bigger than Mars. The time it takes to orbit is 687 Earth days. Okay? And the distance here is roughly 228 million kilometers, 10 to the 9 meters. Okay? And my first question is, what's the mass? A. So you have to use your formula. T squared equals 4 pi squared over gm or cubed. Do we know this? We do. Do we know this? We do. And do we know this? We do. We're looking to get this. So you could rewrite this as m equals 4 pi squared or cubed over gt squared. And just be careful, you have to multiply this by 24 hour and 3600. Okay? I'll give you a minute to use your calculator to give me the m here, please. It should be a big number. See if you can give me the m, please. you get an answer? What did you get?
2.07 times 10 to the 15.
Ooh, too small, I think. I think you made a mistake. Can I see? You forgot the cube
Oh,
and you forgot the square.
alright.
No, square and cube. That's it. So it's 1.99 times 10 to the 30. Okay? And if you don't trust me, you can Google it. It is that. Okay, next part.
I got 1.99.
You got what?
I got 1.99.
You got 1.99? Yeah, that's what I said, isn't it? 1.99?
But the times 10 is away.
Oh, okay. What is the velocity, the v? How fast is this planet moving? So we can use the formula v equals omega r, which is 2 pi r over t. So we know the r and we know the t. So can you give me the v, please? Should be big. Yeah, I think it's this.
What's the units?
It's v, so it's meters per second.
Meters per second.
So I'll change this into 24 kilometers per second. Yeah. Yeah, did you get that? See that? Yeah. So it's moving pretty fast, right? Every second, the planet moves 24 kilometers. Pretty fast. The orbit of Mars is not circular, it's elliptical. At its nearest, it's 207, and at its furthest, it's 228. What is the speeds at this point? Okay, so when will it be moving fastest? Here? Or, oh, I just have one choice. Sorry. Well, where would it be moving faster? Here or when it's 228? 207. So what happens is it's 228 away, but it's not always 228 away. As it comes in, it is only at closest 207 million kilometers. So what happens is, as it spins in, it goes faster. It will be going faster than this. Okay, so what we have here and here, what did I say that was? 228 times 10 to the 9, 228 times 10 to the 9, and this is going at 24 kilometers per second. And then when it's over here at 207 times 10 to the 9, it will be going faster. So R1 V1 equals R2 V2. Cancel. Cancel. So V2 is 228 over 207 times 24 times 10 to the 3. So what's that, please? 26 times 10 to the 3, so that's 26 kilometers per second. Are you okay with that? What did you do in your last class with Connell in exam prep? More mechanics because you wanted to, or and how are the mechanics questions going? How many have you done, do you think? 2 pages is good. Yeah? You think so? Do you feel like you're getting them right or not? Are you sure? You have questions? Good. Because what I was thinking of doing is I'll let you work on this for a few minutes, but I think it would be a good idea if we have a little tutorial on those questions we've been trying with Connell, the mechanics ones. So if there were some questions you couldn't do, I'll do them now for you. All right? Do you know the ones I'm talking about? You said you did 2 pages. So do you feel like you need to see any of those? You got them perfectly. So you
But when I checked
they worked out right.
the marking scheme,
Yeah.
they show you
Okay, okay. Have you got this book with you today or not? No. Oh, or maybe we can't do it. You have it with you today? I'll tell you what day do you bring it in for Connell?
Wednesday.
And do we have physics on Wednesday? No, we don't actually. We have it tomorrow. When's our class after Wednesday? Thursday? Friday? Well, not this week anyways.
I think tomorrow's the last of this week, guys.
Yeah, because we don't have school on Friday. Can you bring this book tomorrow? Because I'd like to give an hour to doing some of these questions you've been trying with Connell. Yeah? Okay. So, anyways, for the next 10 minutes, if you can practice. Now, there's only one question, but it's a big one. It has multiple parts. So this here, this question is like a section B question because it has multiple parts. Now, an example of a section A question might just be like part A. But the whole thing together, that would be a section B question. Okay. So what time are we at? Oh, good. Okay. So if we could just try this until about 2 o'clock, and then we'll see what we'll do in the next class. The reason I'm not sure is I don't know if I want to start the next chapter yet. Or if I want to do some revision. Yeah? Yeah. You know where it's from?
Yeah.
I don't know, some student told me about it from some show. I thought I'd put it in as a joke. Okay, anyways, you can try these now for a few minutes. Yeah, that's the one. Yeah, that's the one.
Yeah, there's it's from the show.
Secret NASA.
Secret NASA sounds unofficial to me, so that's why it sounds weird.
Yes. Yeah, I just put that in as a joke.